Okay, so let's start. Okay, so this is where we left off last time. We talked about kernels, and I want to remind you the big picture and the last two examples we played with. So what we showed is that if we want to make predictions with respect to a separating hyperplane, W, and it doesn't matter now how we learn this W for the sake of this statement. Instead of doing a dot product of our example X with W, we can also write it as a function of dot products of the X we care about with some previous examples. Right? So that's what we said, and that's what we call the dual representation, right? So instead of writing the current prediction as our X dot product with W, we're writing it as a bunch of dot products of our X with previously observed examples, specifically with the examples on which we made mistakes. And then we wrote it this way. We said f of x, our prediction is going to be this linear sum over M, over example Z taken from M, where M was the set of all those examples on which we made mistakes, of this K of xz. K of xz was really the dot product between x and z. We call this a kernel. And S of z is the memorized what type of mistakes we've made on it, whether it was a mistake on a positive example or a mistake on a negative example. So that's what we said last time. Now, really, the reason we developed it is because we want to be able to work with dot product in very high dimensional space. Right? So we think that just working in the original representation that we're given the n-dimensional space is not going to be expressive enough. We want to blow up the feature space. And as an intermediate step, we develop this representation because I told you it's going to be helpful. So what does that mean that we want to work with high dimensional space? So let's take this example. So we have two examples, x and y. Let's think for a second that x is the one that I care about now. I want to know my prediction on x. And y is one of the previous examples that I've seen. So I want to be able to compute the dot product between these two. Now, also, I'm blowing up the feature space. So rather than representing x and y in this, I chose to transform them to a higher dimensional space, in this case, quadratic dimensional space. So I'm going to represent, I'm going to call the transformation phi. Phi of x is going to be this bigger vector here that has 1, the original x, all the squares, and all the mixed terms, xi times xj. Right? So that's a higher dimensional representation of the same example, right? And I do the same thing for y. So instead of n-dimensional space, I have something like n-square dimensional space. Okay? And my goal is, of course, to compute the dot product, because as I said above there, in order to compute the prediction at x, I should be able to compute dot product of x with other previously seen examples. So what I need to do now is compute this A, phi of x, transpose dot product with phi of y. And of course, this is going to take time. That is a function of this n-square dimensionality that I now have. Instead, and this is what we call the kernel trick, I can compute the following thing. I can compute the function k of xy in the following way. I'm just going to compute the dot product in the original space, right? So this is the x here. This is the y. The dot product, this is going to take me only something that is n time. I'm going to add 1 to the number that I get here and square it. And my claim is that these two are going to be the same. Right? So basically, rather than computing A, which is going to cost about n squared, I can compute B, which is going to cost about n. That's the thing. Now, the reason I said coefficients do not really matter is because I'm cheating a little bit. If you really write this down, if you try to take this and write this down, you will get that you have coefficients here. And I omitted the coefficients because it really doesn't matter to us. Anyhow, you're going to learn coefficients for these. But the important thing is that rather than working in an n-square dimensional space, I can do it in an n-dimensional space. Questions? Clear? Okay, second example that we gave. And again, I'm restating what do I mean by the kernel trick to make sure that we are all on the same page. We want to work with degree 2 polynomials, for example. Could be also degree 3 polynomial or degree 7 polynomial or other kernels. Then the dot product will be in a space of dimensionality n squared. Specifically for that case, it was n plus 1 over 2. Which is about n squared. And the kernel tricks allows you to save and compute dot product in the original n-dimensional space. Okay, so So now the question that you could ask is, okay, can I use any function as my K, as my kernel, and plug it in this case? And the answer is no. A function over these two vectors, x and z, is a valid kernel if it corresponds to a dot product in some feature space. So if you want to prove to me that a function is a kernel, you have to show me that, I don't care how you compute it. It can be like 2 to the same xz as we did last time. You have to show me that it's a dot product in some feature space. So let's take, which means this, right? So here I defined K this way, but if you bring K from somewhere else, you have to show me that there is this T of X and T of Z such that their dot product is equal to K. So let's take an example. Here is a function. It's a quadratic function, X dot product Z all squared. And you want to say, I want to use this as my kernel. Okay? Is this a kernel? So going back to the definition that I gave just above, a function is a valid kernel if it corresponds to a dot product. I need to show you that this function indeed corresponds to a dot product. Written this way, it doesn't, right? You don't see it's a dot product. It's a square of some number, and this number happens to be a dot product, but by itself, K of xz isn't a dot product, the way it's written here. Everyone agrees? So let's write it as a dot product. And I'm doing it in an example. I'm just assuming that x and z are two-dimensional vectors, so it will be simple to write. So if x and z are two-dimensional vector, then your definition here of dot product x transpose z can be written this way. It's just x1 z1 plus x2 z2 all squared. That's your definition of K of xz. Let's rewrite it. I'm just opening the parentheses and I get this. And now I'm claiming, and this red equal sign here is the claim really, that I can actually write it, this expression, as a dot product of these two vectors. Here is one vector, x1 squared, comma, square root 2, x1, x2, comma, x2 squared, dot product with the same thing for z. Okay? Just 1 second. So basically, I came up with this representation, and now my claim is, okay, now I showed you that this k function is indeed a dot product of two vectors in a three-dimensional space. Let's call this a phi, and therefore k is a kernel. Yes?
When you say the kernel corresponds to a dot product, what does that mean? Does it mean
It's exactly what I mean here. It is a dot product.
Okay.
So I defined it just, some way, this way. And in order for it to become a kernel and enjoy all the properties, the fact that you can run the algorithms with it, I have to show you that it corresponds to a dot product, and I showed here that I can write it as a dot product of two vectors in a three-dimensional space. Okay, so before I started with a dot product in a blown-up space and computed the kernel in a more efficient way. Here I went backwards. I started with some function that is efficiently computed, like this one, right? It's just, I can compute it easily in the original representation of x and z. And I showed that it's okay because it really corresponds to a dot product in a higher dimensional space. Okay, so we have a definition for a kernel. We have a condition of when something becomes a kernel. Now, it's not the only way. So, okay, so what we proved here is that K is a valid kernel by explicitly showing that it is a dot product. Now, it's not the only way. really, and by the way, this is the example that we started with last time. And the kernel that I show here is exactly the kernel that you need in order to take this data and actually learn it with a linear separator, with a perceptron. Now, it's not the only way, as I said. So a comment here. In general, you don't necessarily have to show this feature function phi that I showed here, for example, phi of x and phi of z. There's another condition that is more general. You can construct a kernel matrix by looking at the values k of x I zj, so it's going to be a matrix, and the ij entry there is going to be k of x I zj. If this matrix happens to be positive semi-definite, which I'm not defining here, most of you have seen it, it's a kernel. Now, we won't care about it. There are some hidden slides here that you can go through if you care about it, and you'll see some more details. From our perspective, we can take the definition that I've given here and say something is a kernel if I can write it as a dot product of two vectors. Now, kernels have a lot of properties. Here are some examples of kernels and that will allow us to play with some properties. So I already mentioned the linear kernels. That's basically just the dot product. I should have had transpose there. Polynomial kernel of degree d. We've seen the case of d equal 2. Polynomial kernels up to degree d. We've seen this example also with d equal 2 and c equal 1. So these are kernels. And in fact, we've proven that these are kernels. Now, if you have a kernel, you can construct other kernels as functions of it. For example, you can take a kernel, multiply it by a constant, it's still a kernel. You can take a kernel and multiply it by a function that applies on x and on x prime, it's still a kernel. You can apply a polynomial on a kernel. So you can define k prime as a polynomial with the argument k. And you can exponentiate a kernel. So you can define k prime as e to the power of a kernel, and this is a kernel. Now, if you really wanted to show that these are kernels, let's take the first example, the simplest one at the top, multiplying a kernel by a constant. You can go directly from the definition. So you know that k of x, x prime, is a kernel, which means that there is some phi such that k of x, x prime, the one at the top here, can be written as phi of x dot product phi of x prime. And therefore, I would argue that also there exists some phi prime that allows you to do it for k prime. Basically, define phi prime to be square root of c times phi. And then you will get that the dot product of phi prime of x, phi prime of x prime is this k prime. So in all these cases, you can go directly from the definition and convince yourself that these are kernels. And you can do other things in order to construct kernels. You can add kernels, you can multiply kernels, and so on. So I'm not going to go over all these details, but basically, basic operations over kernels maintain the fact that it's a kernel. And in all these cases, you should be able to convince yourself directly from the definition. Okay, here is one important kernel that I want to spend a couple more minutes on. It's a Gaussian kernel. So the kernel is defined this way. K of xz is e to the power of the negative sign of x minus z squared divided by some constancy. So it's going to look something like this in the xz space. So think about this. So x minus z squared is just the Euclidean distance between two vectors. You've seen this before. You can think about C as some free parameters that is going to allow us to scale this kernel. And then let's see what happens. If C is tiny, then this matrix actually is going to be 1 on the diagonal, or a fixed number on the diagonal, and 0 outside. So whenever x and z are different, it's going to be close to 0. Whenever x and z are the same, it's going to be 0 there. So it's e to the minus 0, which is 1. If c, on the other hand, is very, very large, you will basically get that all the items are the same. It really doesn't matter what happens. In general, what you get for a middle range C is that as x and z become close together, the value of this kernel is going to be higher. So you're going to get some kind of a Gaussian that will scale with C. So essentially, it's a way to increase the dot product when your z that you've seen before is close to x, and if it's farther away, you don't want the dot product is going to be 0. Yes?
What x and z are vectors, right?
X and z are vectors.
So are you taking the norm of their difference and then squaring it? Or, because you can't just...
You're right, actually. I'm sorry about this notation here. Yeah, it should have been the size of this. Yes, yeah, I'll change this notation. Yeah. It's the size. Okay. Okay, so once we have a definition, I want to go through the process of, I called it a Gaussian kernel, but is it really a kernel? So again, what we can do is we can start with kernels that we know, apply sequentially all the operations that I claimed earlier maintain a kernel being a kernel, and convince ourselves that this is also a kernel. So in this case, I'm rewriting this. So what did I get here? So this is just algebra. So I'm taking, this is e to the negative sign of this divided by some fixed number. I'm opening the exponent here. So it's e to this power times e to this power times e to this power. And then I'm writing this as, I'm leaving the one in the middle. This is only a function of x. This is the same function of z. So I can write it as f of x e to the xz divided by a constant times f of z. And then now I can argue that this is, the one in the middle is actually a kernel. Why is this a kernel? Because x dot product z is a linear kernel. We can multiply it by a constant, and we can exponentiate a kernel. So the stuff in the middle is a kernel. And then multiplying a kernel by the same function, left and right, remains a kernel. So basically, these 1, 2, 3, plus multiplying it by f of x and f of z on the both sides are some of the construction operators that I listed before, and therefore, what you get here is a valid kernel. Okay, the last comment here should have come separately. So there's one difference between this kernel and the discrete kernels or the polynomial kernels that I discussed before, in all the cases when we talked about before, for example, if you think back about the polynomial kernel that we talked about, this polynomial kernel or this polynomial kernel, too fast. Okay. I have these two representations here, right? So I have the original representation x and z, and I have the blown up representation, in this case only blown up to three-dimensional space, phi of x and phi of z. And I have the choice of working in the original space, just maintaining my w, or if I want to work in the blown up space, I have two options. I can just blow up the feature space, take this vector as my representation for x, take this vector, the phi of z, as my representation of z, and just work as usual with the w, what we call the primal space. Or equivalently, I can work in the dual space, and then I'm going to work with the kernel, which means I'm going to work in the original space, but feel as if I'm in the dual space. So I have these two options, and they're completely equivalent. We went through this algebra last time. So basically, you can either blow up the feature space and work in the primal space with your W, or work in the dual space and actually do your computation in the original space, but really work in the blown-up space. When you work with continuous kernels like the Gaussians, you don't have this option, because really the equivalent space is infinite dimension, so I cannot say that I have these two options. If you want to work with a Gaussian kernel, you have to work with a Gaussian kernel. You cannot explicitly write down the feature space and just work in the primal space, maintaining your W. So this is the key difference between these. Okay, so let me summarize and say a few more things that, in fact, some of you have asked last time. So what have we done? We gave a method to run perceptron. We'll see later on that other algorithms can do the same thing. SVM will be our example. Run on a very large feature set, or very large dimensionality, without incurring the cost of keeping actually a very large or very high dimensional weight vector. We really showed that we can compute the weight vector in the original feature space. Now, I commented last time, and it's really an important comment, that this really pertains only to efficiency. I mean, we actually haven't done anything that makes learning better. We just rewrote algebraically the representation. The classifier that you will get is identical to the one that you would have run in the original feature space. So you haven't touched generalization, whatever that is, right? So if you were doing well on future examples in the W space, you will do as well in the dual space and vice versa. Yes?
How do you do it when you're in a big enough feature space to where you can check the W?
Yes, I'll get to it in a second. So that's really one of the key questions here. I mean, do I want to do it or not? So as I said last time also, kernels were popularized. I mean, kernels is a concept that came from functional analysis, was there many, many years ago, were popularized in the context of support vector machines, but really apply to many, many models, as I shown it in the context of kernel perceptron. They apply to Gaussian models, to PCAs, and many other models. Some of you may have seen this. Some may see it later. Okay, so now there are two questions for us. One is, do I want to work in the dual space or not? So let's assume I decided that I want to blow up the feature space. So there are two decisions here. One, do I want to blow up the feature space because I'm not happy with the expressivity of my current representation? Think again about the circle of the green and blue points, or this curve. Do you want to stay in the original space, or you want to blow up the feature space? That's one question. The second question, let's assume you convince yourself that you want to blow up the feature space. Do you want to use the dual representation, or do you just want to blow up the feature space and work with your W, which I'm going to call the primal representation? So here is a back of the envelope computation that gives us some intuition for when do we want to do what. So let's assume I have M examples. I have the dimensionalities of the spaces, or the feature spaces, are T1 and T2. So T1 is the dimensionality after I blew up the space, the dual, and T2 is the original dimensionality before I blew up the space. The other way around. So T1 is the dimensionality in the dual, which means it's the small dimensionality that I have. And T2 is, if I blow up the feature space, I really have to, and I work in the primal, I actually have to pay the cost of the blown up feature space. So in the quadratic example that we gave before, T1 is n. It's my original dimensionality. And T2 is going to be n squared, the size of the blown up space. So another way to think about T1 and T2, this is the cost of the dot product, right? So if you are working in the dual space, the cost of the dot product is T1, the original dimensionality. If you blow up the feature space, but you stay with your W, you're going to suffer the blow up dimensionality. The cost of a dot product is going to be T2. So what is the computational cost of the whole algorithm? So in the dual space, what do I have to do? How many dot products do I have to do overall? So let's assume I want to make predictions on all my M examples. What is the cost of doing a dot product on one example?
Original feature dimensions into the number of mistakes you made before that example.
Right, so it's the T1, which is my dimensionality. But I have to touch all the examples I've seen before. Right, so I have to do dot product order of m times. Maybe only a half of them I made mistakes, but I'm going to think about it as m. So, so for one example, I have to touch all the other examples, right? But I want to touch all the examples, so this is actually m squared dot product that I have to compute. For each example, I have to touch all the other examples. I have m examples, so it's m squared dot product. Okay? And each one of them, each one of the dot products is going to cost me T1. Everyone is fine with this? M squared comes from the fact that each dot product, each example has to be I have to compute the dot product with all other examples. And because I have m example, this means m squared, order m squared dot products. In the dual, what you have to do is for each example, you compute the dot product with your W, and that's it. So m times, because there are m examples, you compute the dot product with the W, it's going to cost you, each one of them is going to cost you T2. So in the primal space, where I'm doing the W, my cost is T2m. In the dual space, where I'm doing this k of xz, I have m squared times t1. That's the order of magnitude. Now, typically, t1 is going to be much, much smaller than t2. The examples that we've given ranges from n and n squared to n and 2 to the n. So basically, it boils down to the number of examples one needs to consider relative to the growth in dimensionality. So if m is very, very large here, if m is huge, you don't want to be here, because here you're going to suffer m squared. You much rather do this. So even though you blew up the feature space, you are willing to pay for each dot product more, because you're going to do a lot less dot products. On the other hand, if you have a small number of examples, it's okay to do m squared dot products, because each one of them is cheaper. So that's basically the trade-off that we have. Yeah.
And when you say, like, the scale of this, I guess in my mind, the dual space makes sense for, like, language processing, because the text that you have in reality is a lot of times smaller than the parse vector that you have.
Yes and no. So basically, plug in number and see, right? So plug in for T1 and T2 something. Plug in for M. Sometimes we have hundreds of thousands of examples. So M is going to be 100,000, which means M squared is order of 10 to the 10. Maybe you don't want to do it. In fact, so my last comment here, most people in the language domain will use explicit kernels. They will actually work in the primal space. They will blow up the feature space and work there. And they will tell you that they use linear kernels, which basically means we actually use the explicit feature space, no kernels. But basically, that's the trade-off that you have. So that was one of the issues, right? So we talked about, do I even want to use kernels? And if so, which ones? And if I do want, or do I want to blow up the feature space? And how much do I want to blow it up? That's one. And two, if I do want to blow it up, do I still work in the primal space, or do I move to the dual space? So we answered the second one. We can also answer the first one. It's a little bit harder. And the question here explicitly is, do we want to use the most expressive kernel we can? Right? So you start with an n-dimensional vector. Do you want to use a quadratic kernel? Do you want to use polynomial of degree 3, 4, 5, 6, 10? How do you know which one you should use? Maybe I should just choose the most expressive I can, because clearly it's going to fit my training data. The answer is you don't want to use the most expressive you can. Hopefully this is where your intuition is too. And just because you're going to overfit the data. And it's also possible to give simple arguments analytically that show that essentially what are you doing if you're blowing up the feature space? You may add a lot of features that are completely unimportant, are not needed. And you can show that irrelevant features do not help. So there is a hidden slide there that shows this analytically. I'm not going to go into it. So let's summarize and see if we have questions. So kernels is still a very active field, because in some domains you want to be able to do this. You want to be able to to increase your expressivity. And people define kernels over many structures. For example, you can define kernels over parse trees. So if your X, your input, is a parse tree of a sentence, you can define kernels that essentially looks at all the sub trees of the parse tree and does conjunctions among them, kind of like as we did conjunctions between xi and xj. And you can develop kernels for a lot of structures and a lot of input representations. There is a pointer there if people want to follow a discussion of kernels over parse trees. Questions on this? Yeah.
I'm not exactly sure how we construct a matrix from a kernel. I mean, can you maybe show an example?
I give you two vectors, x and z, n-dimensional vectors. So k of the function k is defined. So I have m examples. Take the ith example. Take the j example. The kernel is defined over these two. Kij is going to be the value of the kernel given the ith example and the jth example.
Matrix's dimension would be the number of examples.
The number of examples.
Cross the
Square matrix of the number of examples. Okay, so for each pair of examples, I can compute the value k of xz. Right?
But I don't understand why we have the number of examples coming into this. I mean,
that's the way it's defined. It's basically given a set of examples, I'm defining a kernel.
the kernel definition is independent of the examples, right? For example, if you have the radial basis kernel, it will have a matrix irrespective of what examples we're training it on, right?
No. So the kernel matrix is a function of the examples that I see. The ij entry in the kernel matrix is the value of k for these two examples. So it's a function of the examples. So in fact, if you really think about it carefully, I kind of cheated a little bit when I said my last comment here that, not this one, here, where I said that unlike discrete kernels, here we cannot easily explicitly blow up the feature space. Really you can, because once I give you a finite set of examples, you can actually compute the kernel matrix. But still people think about it as an infinite dimensional thing, which is not. It's really a function of the examples that you have. So the kernel matrix is a square matrix over the examples that you're given. Other questions on this? Yeah.
I just want to clear the notation. So which is the dual space, which is the primal space?
So the primal space is the standard stuff that we're doing all the time, where you have a W. And you compute the prediction as dot product W X. The dual space is where you compute the prediction with the dot product of your current X that you care about with previous examples. Okay? That's the dual space. So the first slide that I started with today also defines this again. Okay, so basically we played in this space, right, of function that can be made linear. That's not the only way to make function linear or to increase expressivity. In a couple of weeks, we're going to get to multilinear neural networks, which will take our perceptron and stack them together. And you will also be able to think about this as a way to do this. So if you think about what you see here at the top, kind of the 5 nodes at the tops, these two you can think about as output nodes, and these are the input nodes and these are perceptrons. Each one of these is a perceptron. And the representation of each one of the input node could be viewed as a function of other things. So, and this is going to be the role of the network underneath, it's going to transform the representation of the original examples to something else and serve it as an input. So essentially what we're going to do is we're going to use linear units as our basic units. Everything that we've done so far is going to be our basic units. And you could view this as stacking as a way to re-represent the input. So this is something that we're going to get to in a couple of weeks. What I want to move on to now is our next chapter, which is why machine learning works. So before we get to why it works, I want to include some reminders. Okay, so midterm in a little bit less than 2 weeks. Closed books. There will be examples if they're not there already on the website. And we cover everything until next Wednesday. I suggest that you go to the recitation, go to the office hours. We're going to cover the previous exams there. I want to remind you, homework 2 that you're working on now. So one interesting issue that happens in homework 2 that some of you already got to and some of you haven't is the issue of efficiency. So you will see, if you haven't yet, that the way you implement your average perceptron matters. People have already run on the second data set, on the name entities. Yes, no? Who managed to run already on the name entities data? How long does it take? Okay. That surprises me, 2 to 3 minutes. I was expecting to hear either 10 seconds or a few hours. So depending on your implementation, it could vary a lot. And the reason we left it this way is because we wanted you to think about the implementation. So this is one thing, one of the challenges here. So I see at least that most of you are not there yet. Hopefully you'll get there quickly because it could take you some time to think about it. Questions on the homework? No questions. Okay. So where are we? I mean, we talked about algorithms. We talked about learning models, online learning, mistake-driven learning. What do we know about generalization? So what do we know about, is the algorithm good or bad? So what I'm going to do the rest of today and next time is try to develop a theory of generalization. So why do we care about this? So machine learning in the 80s was something like this. People develop an algorithm. They run it on a data set. It works. They're happy. It doesn't work. They're sad. They try something else. That's it. Machine learning in the 2020 is almost the same because people forgot there's actually theory for learning. Most people forgot, not everyone forgot. But really, what you want to be able to do is you want to develop algorithms that come with some guarantees, right? So most of you are going to use machine learning somewhere, build bridges with machine learning. You want to make sure that the bridges actually are going to stand there. So, the Romans managed to do it 2,000 years ago, and we have guarantees that when you build something, it's going to stand. And we have some conditions on what is it going to withstand and what it will not. We're not there yet with a lot of our software in general, machine learning in particular. And the question is, what can we say about what's going to happen in the future, right? So this is really the key challenge. So this is really an important part of this class, and I'm going to just give you a glance into this theory, just that you know that it exists and what are the issues that are involved in doing it. But I'm hoping to convince you that this is really important, that you should care about it, that you should be able to understand why learning works, when it works, what does it depend on. So when you see an algorithm that fails to generalize, you kind of understand what are the issues and maybe what direction you should go in order to think about it. Okay, so really what we care about is, are there general laws that constrain inductive learning? Are there problems that we actually cannot learn? Cases where we cannot learn? Is there a notion, a well-defined notion of learnability that says these functions cannot be learned, this function can be learned? And when can we trust the output of a learning algorithm? Is it just coincidental that we got, on this example, the right prediction? What's going to happen on the next one? So we want a theory that relates a few of the important components here. The probability of successful learning, the number of training examples that we've seen, the complexity of the functions we're learning, the hypothesis space, the accuracy within which we approximate the target function, and also the way in which the examples are presented, the learning protocol. So we already talked a little bit about it. I mean, we had one short section of quantifying performance where we talked about multiple learning protocols, right? We had this target conjunction as our example, and we played with it with 3 different protocols. Protocol 1 and Protocol 2, we actually showed that we can learn exactly, and we even quantified how many examples are needed. The same thing we did for Protocol 2. And again, we saw that this is a better protocol. Of course, requires a teacher. But again, we could learn exactly. And then we got stuck with the third learning protocol, which is in some sense a more natural, or at least became more natural over the last 25 years of machine learning work, or maybe 35 years even. The problem there was that we didn't learn exactly, right? We knew, because I told you that the real function, the hidden function, is up there, and the final hypothesis that we got was a little bit different. We had the x1, and we had the discussion of, is this good? What does it say about our performance in the future? What does it say about number of examples? And so on. So the bottom line, though, was that we only learned an approximation of the true concept. We did not know how many examples we need in order to learn exactly, or to be happy with what we learned, because we only quantified it in terms of how many mistakes we're going to make. We don't know when we're going to make these mistakes. And we want to go beyond this. So after this section, I told you there are 2 directions, right? So we can either go to talk about mistake-driven algorithms, which we have done, or we can continue to analyze this probabilistic intuition. And here is the probabilistic intuition that we developed then. So we said, well, x1 is still there in the hypothesis that we learned. But during our long training process, we have never seen x1 in a positive example. Therefore, that's the reason we didn't eliminate it. So we can assume that this event, that x1 is on and the example is, the x1 is off and the example is positive, is a low probability event. And it's going to be a low probability event also in the future, and therefore we're not going to suffer too many mistakes. So this is an intuition that leads to the PEC framework, probably approximately correct framework that will allow us to think in a quantitative manner about how well are we going to do. And that's what I want to do now. So just very brief reminder, we're talking about of terminology. I mean, you all know this already. Instance space, concept space, hypothesis space. We're going to use all these. And our goal is to find a hypothesis, H, that is the same as the target function, F. And we already said, what does it mean, the same? Where is it the same? Is it the same on all the example in S? Or is it the same on all the examples? And of course, it's uninteresting if it's only the same on all the examples we've seen in S. And it's unrealistic to assume that it's going to be the same for all instances we'll ever see. And this is the game that we want to play here. We want to be able to understand, so what are reasonable expectations that we have? And probably reasonable would be to approximately be similar to F. And we'll see what exactly we mean. So here is the example that we played with before. We had a function. The blue one is the function, the target function. Think about it in the following way. This rectangle is the set of all examples in the universe. Let's say in our case, all Boolean examples. Inside the blue circle are all the positive examples of this function. Outside the blue circle are all the negative examples of it. And the same thing with the red. The red is my hypothesis. Inside the red circle are all the positive examples of the hypothesis. Outside, all the negative. Okay? So the region that I point to with the arrows are the regions where examples on which F and H disagree reside. Okay, so what is the game we're playing here? We've seen many examples drawn according to some distribution. Since all the positive examples, in all the positive examples, X1 was on, it's very likely that it will be on in future positive examples. That's the way we're thinking here. And if not, in any case, X1 is active only in a small percentage of the examples, so our error is going to be small. So the error that we're making, which is basically the area of these two moons, right, where F and H disagree, can be written this way. Now notice this is not a uniform distribution necessarily, right? So I don't know what is the distribution over these. Maybe some regions are heavily supported and some are not so heavily supported, or maybe not supported at all. But what I care about is the probability under this distribution that f of x differs from h of x. Now, in the case of this example that we've seen, is this the right picture? In the case of this conjunction? Or should I draw a slightly different picture? Yeah?
Will one of those gaps, so either the left one or the right one, not exist?
Which one?
I don't think that for a second.
Okay, so someone else wants to think about it? So the claim is that one of these moons shouldn't be there. Yeah?
Is it the, like the moon, the space to the left, basically, because your function, your h, covers a larger area than f.
So basically, what you're saying is that this area, which means positive examples of f that are negative for h, do not exist.
Yeah, because if you make mistakes only one type of example.
Which mistakes can we make? Which means we're going to say no where the example is yes. When are we going to say no? Give me an example where we're going to say no where it should be yes.
X1
where x1 is there, and it could be a negative example, right? So basically, even though I drew it this way, the support on this region should be 0. But still, this is the general case that we care about the weight of when f disagrees with h. In our case, it's actually this way, right? So it's a little bit different than what we said before. Why?
The previous figure, we drew two things. If they were sets of real valued numbers, then that would hold good. But this is Boolean, so we can make mistake on only one of them.
No, we're always Boolean. But let's think about why is this the right picture. So basically, what am I claiming here? I'm claiming here that there are positive examples. For example, the example where x1 is 0, x2, 3, 4, 5, and 100 are 1. All the rest, I don't care. This example is positive, right? So 0, 1, 1, 1, 0 and all the rest ones, for example, is a positive example. But my hypothesis is going to think that it's a negative example. So it's actually going to be here. Everyone agrees? So, and the question for us, once we agree with this, is what's the probability that's going to happen? So what I want to do now, so we agree on kind of qualitatively what's going to happen, what type of mistakes we're going to make, and the question is, can we analyze it and say what is the probability this is going to happen, and what this probability depends on? So let's try to do this analysis. So let's z be one of the literals. Literal means one of the variables that we have. And I'm denoting by P of z the probability that when I sample an example, according to my distribution D, which I don't know, but it exists, this z is positive. Sorry, the example is positive, but z is false in it, which is the case for x1, right? What I care about is this event where the example is positive, but x1 is false in it. So I'm going to denote this event, the probability of this event, by P of z. So first of all, my claim is that the error of my hypothesis is bounded by the sum of P of z, where z ranges on all the hypotheses. Because that's the worst that can happen, that each one of the hypotheses, the elements, the literals that stayed in the hypothesis could cause a mistake like this, right? In this case, we know the truth. We know it's x1. But in principle, when you have a hypothesis with some variables, each one of them could cause these mistakes. That's the worst case. So my error is going to be the sum of P of z's, sum over all literals in the hypothesis. Now, during learning, really P of z can be thought about as the elimination probability, right? So it's the probability that a randomly chosen example is positive, and z is deleted from the hypothesis because of that, because z is false in it. Now, if z should be in the function, P of z is 0, right? Because it's never going to be the case that the example is positive and z is false in it. Okay, so for the true one, like x3, P of z is 0. Everyone agrees? Okay, so now, first of all, we would agree, I think you would agree on this claim. H makes mistakes only on positive examples. Here is why. It makes a mistake only if a literal z that is in H but not in F, like the x1, is false in a positive example. In this case, H will think that this is a negative example, but really it's a positive example. So that's the only case we're going to make mistakes. And therefore, we can say that P of z is also the probability that z causes H to make a mistake on a randomly drawn example. As I said, there could be overlapping reasons. I mean, it could be that in one case, one example that we made a mistake on causes us to eliminate two z's, but worst case is that they occur separately, and therefore this is the right bound up there on the arrow. Okay, so now that we have this, I'm going to call a literal z a bad literal if this probability is greater than epsilon over n, where epsilon is some small number. We will choose it later, let's say 10%, 0.1, and n is the number of variables that we have. I'm going to call it bad if p of z is greater than epsilon over n. Why is that? Because this way, I can bound the overall error to be less than epsilon. That's my goal. I want to make sure that the overall error, remember that I defined here, error of h, I want this to be less than epsilon. We'll choose epsilon as you wish. So what is a bad literal? Is a literal that is not in the target concept. If it was there, p of z would have been 0. It's not in the target concept and has a significant probability to appear false with a positive example. Now, really what happens? Okay, so first, if there are no bad literals, my error is less than epsilon. The reason is that the error is less than the sum over all elements in the hypothesis of p of z's. All of them are going to be less than epsilon over n. So definitely the error is less than epsilon. What if there are bad literals? What if there are some literals that have significant probability to appear false in a positive example? So let's assume that z is such a literal. What is the probability that it will not be eliminated in a given example? So there is some, like x1, it's a bad literal. What is the probability that we've seen an example and it wasn't eliminated in it? It's 1 minus p of z, by definition of p of z. Now, what is the problem with this x1, or in general with a bad literal, is that I've seen many examples and it wasn't eliminated. It's still there in my hypothesis. What's the probability that I've seen m examples and it's still there? It's going to be 1 minus, okay, so this one is less than 1 minus epsilon over n. But what's the probability that it will not be eliminated by m examples, which I assume to be independent examples? So the probability is going to be 1 minus p of z to the m, which is less than 1 minus epsilon over n all to the m. So it could happen that some literal that I call here a bad literal survives m examples, was not eliminated, but the probability that this happens is less than 1 minus epsilon over n to the m. Now, what do I want? I want this probability to be small. Now, this is for one literal. Overall, there could be n literals that are bad, so the probability that some bad literals survive m examples is bounded by n times this, 1 minus epsilon over n to the m. And my wish is that this is going to be a very, very small number. If this is a small number, then I'm not going to worry on the appearance of one of these in future examples. So I want this probability to be small. Say I want to choose m large enough such that the probability that some m survive m examples is less than delta. And again, delta is going to be some small number, let's say 5% that you choose later. So, so basically, that's what I want. I want the probability that Z survives M examples, was not eliminated in any of them, to be, which is this probability, to be less than delta. And now what I need to do is I need to isolate M from this expression, and this will tell us how many examples do you want to see so that this will happen. So I'm going to use some inequality here. It's always the case that 1 minus x is less than e to the minus x. If you want to convince yourself, you can write the Taylor expansion of e to the minus x. You've all seen that. And therefore, I'm replacing this 1 minus epsilon over n there by e to the minus e to the epsilon over n here. So what I get is that what I really need is to require that n times e to the minus m epsilon over n is less than delta. And from this, you can take log of both sides. I took log base e, natural log. And then what I get is that m has to be, so you'll do this algebra, m has to be greater than n over epsilon times ln n plus 1 over delta. So if I take these many examples, I guarantee that the probability of failure, the probability that my error is greater than epsilon, is less than delta. Okay, so before we get to some numbers, let's see what did we do here. So essentially, we know that we cannot learn exactly, right? We know that our learning algorithm, and we took a specific learning algorithm, but we can generalize it to general learning algorithms. The function that we've learned, the hypothesis, is going to be some approximation of the true hypothesis, of the true function, f. What we want is to quantify how good is it going to be. And what we want to say is, tell me how many examples do I need to see so that my error is going to be less than epsilon. That's the goal. Now, what I told you is I cannot guarantee completely that your error is going to be less than epsilon. But what I can guarantee is that with high probability, at least 1 minus delta probability, your error is going to be less than epsilon. So I have this delta and epsilon. Epsilon is the error that I will make in the future. And delta quantifies how certain I am that I'm going to have error less than epsilon. I need both. And what we showed is that if I take these many examples, and these many examples should make sense to you, right? Because it basically goes up with the dimensionality. Higher dimensionality, more literals that could cause you trouble. It goes up with 1 over epsilon. If you want small error, you need to see more examples. And it goes up with delta, with 1 over delta, which means if you want to be very confident about it, also you'll have to pay and use more examples. And you can plug in some numbers, which I'll do in the next slide, and you will convince yourself that this is okay. So, but basically what I want you to understand is this theorem. So if m is large enough, as above, with probability at least 1 minus delta, there are no bad literals. Or, equivalently, with probability at least 1 minus delta, my error is going to be less than epsilon. So basically what I showed here is that we can use the same algorithm as before and quantify how well we're going to do in the future, and basically give you guarantees as a function of how many examples you're willing to look at that the future is going to be good. You're not going to have error that is larger than something. Okay, so we're going to continue with this and generalize this a little bit next time. Questions? Okay, see you next week then. Yeah.
So for like generalization exams, you have like KX, and you have a learning function.
Yes.
And Z is belongs to M, which is like promotion and demotion.
Yes. The example in which I made mistakes.
Okay.
Yeah.
Yeah. So I'm basically wondering, yeah, would that, I mean, would X and Z be the same, like most times, except one is like not making mistakes.
No, X and Z are just examples. Right? So, so you ran the algorithm for some time,
Yeah.
and now you are at the stage of the algorithm where you see example X and you want to make a prediction on it.
Yeah.
How do you make this prediction?
Based on the mistakes.
Right. So you have to compute f of x.
Yeah.
And what we showed is that f of x can be computed as a function of the examples on which you've made mistakes before.
Yeah. But since you like dot product X and Z, right?
Yeah.
And would X and FZ actually be the same value? Because I mean,
No.
they're
I mean, z is one example, x is another example.
okay.
So I don't know. Could be that, f of x is a positive example and f of z is also positive, or could be negative. So I'm not sure.
Okay.
And really, it doesn't matter because I'm going to do this for many z's. Some of them are going to be positive, some of them are going to be negative. So I don't know. And for the computation, it doesn't matter.
But you're taking I from the subset of M and versus I from the subset of the entire data set, right? When you're looking through, would that be going through the same example? Because Z is also taking the training data.
Z is, so we gave it for the case of perceptron. So think about, you have an ordered list of all the examples, right? So you started with the first example, you went, so Z is, say, example number 100.
Yeah.
And it so happened that on Z you made a mistake. So you write it on the list of examples on which I made mistakes. And then you got to example 250, which is my current X, and I want to compute what is the prediction on this. So what we've shown is that you have to compute the dot product of X with all the examples on which you made mistakes, including this Z, which was X100, and then do some weighted sum of them. And this will give you the prediction on X.
Okay. Got it.
Okay?
Thank you.
Hey, I had an idea I wanted to run by you. So you know the poverty of the stimulus argument?
Yeah.
So that never sat well with me, and I was always thinking, I feel like if you were to take, just sort of as a thought experiment, you took a bunch of linguists and shipped them to a new language that they'd never heard before and give them all of the input that, say, a standard 4-year-old would get in their first 4 years of life. I mean, maybe this is just a bad intuition, but my intuition would be they could probably do a pretty good job constructing the grammar of the language just with the positive examples. And I was wondering if it wouldn't be worth trying to simulate that. So seeing if you could feed an algorithm what you could call a reasonable model of what a 4-year-old might get as input, and see if it can't start generating some pretty reasonable sentences, or at least recognizing what is a valid sentence and what isn't.
So there is a lot of work in this direction by developmental psycholinguists that are thinking this way. They say, okay, so how come kids can learn language so fast? What are the models that we need to have so that it mimics performance that kids can get when
Right.
they're 3?
And I think crucially, I would want to have a model that doesn't require any previous innate knowledge. I think that's nonsense.
Okay, so first of all, there is a lot of debate on that.
I know.
I think most people today will think that there is something innate. There's something that is innate does not have to be any grammar or even language-related thing, but it's some learning mechanism
Yeah, sure. Of
that
course.
allows you to do something.
But that would be the model, right? So that doesn't require you to have.
Yes, but it's probably highly related also to you cannot put people in a box and feed them with text or speech and expect that they learn language. There's probably a lot to do with interaction with the world, with various signals that they get. It's not only positive examples, right? They get signals that indicate to them that this is that and not that.
Right.
And when they say something, they get feedback that says, you said it wrong. So there's a lot of work in this direction. So in fact, I also work in this direction. There's a data set, it's called Childes, huge data set of conversations between moms and kids, different ages.
It's huge.
All the way up to, I think, age 6, something like this. And a lot of the research in this area goes by interacting or sort of playing with this data set. So yes, so people are working in this. We're not successful, let me tell you that. So in very specific cases, so we have a paper that where we argue that we have a model that can mimic mistakes kids are making when they're, 18 months, and then recover from it, just like kids do when they're 24 months. But this is a very specific kind of narrow case in the case of basically understanding verbs, understanding arguments of verbs. This is the subject of the verb, this is the object of the verb, this is the temporal argument of the verb, and so on. So in this scenario, we can show that we can make mistakes, just like very young kids, and recover from it once we see more examples, just like they do when they're 24 months or something like that.
Right. Well, that sounds a little bit hopeful.
Yeah, I think it's a very, very interesting area of research. And I can point you, if you go to my publication page, search for baby SRL.
Okay, what's
Baby,
SRL stand for?
SRL stands for semantic role labeling, which is basically one of the tasks that people are doing when they look at verb, understanding predicates in sentence.
So in this case, the role is subject or object or
Yes,
directed.
yeah,
Okay,
yeah.
gotcha.
And we do it relative to predicates, which are verbs. So there is, we have a couple of papers, probably the most interesting one is, there is a survey paper or something like this, a long paper on baby SRL that will explain this line of work. So we are actually continuing with this. I think there's a lot of really interesting questions there. So you can take a look.
Cool, I will.